All right. Hi, everyone. My name is Michael. I'm the co-founder and tech lead at Boltz, and we do submarine swaps and all kinds of atomic swaps between the Bitcoin layers. And one of the most important layers for us is the liquid network, which is why I'm here today. And I want to tell you a little bit about what I do, what we do, and a little bit about liquid in general too. But before I talk about Boltz and how we do the liquid swaps and lightning swaps and all these kind of things, first I want to talk a little bit about liquid itself. And as you can see on the topic of my presentation, I want to compare Elements, the software that Liquid is running on, with the EVM, the Ethereum virtual machine. And maybe to get started, I want to ask who here has used Solidity and like the Ethereum RPCs and like programmed on top of the Ethereum ecosystem? Maybe with a raise of hands. Okay, like 2 people, which is not that many, but regardless, I want to tell you a little bit about it, because the huge promise of the Ethereum world has always been the programmability and the construction of a new financial ecosystem on top of their virtual machine and Turing completeness and whatnot. But with Elements, which is Bitcoin, but with some extra new features, you can also build pretty strong primitives and have pretty good programmability. And today, I want to start off with a little comparison of what does the EVM world look like, what does the Elements Bitcoin-esque UTXO world look like, and especially have a focus on how Elements differs from Bitcoin, what the extra features that exist in Elements today can be used for, and what kind of financial primitives and scripting capabilities those new features in Elements allow us to do. So, first of all, the most important thing to understand is when you look at the Ethereum world, Tron, Solana, whatnot, those are account-based. So singular addresses, while Elements and Bitcoin is UTXO-based. That's like the most fundamental thing to understand. And everything that you program on top of those chains, every time you use them, this is the one thing that's like the fundamental, the base of it all. UTXOs, unspent transaction outputs versus accounts. So let's have a look at what those things even mean. So in the UTXO model, what you have is transactions, and transactions have inputs, basically what you are spending, and you create new outputs. And every input, apart from Coinbase transactions for miners and whatnot, which is basically irrelevant for us, has a previous output. So when you have an input in your transaction, that input must have been the output of a previous transaction. And in my little graphic, I have it this way with like a lock and a little X, which means that this was an output, and the X means we destroyed by adding it into our input of our new transaction. And to destroy the previous output, we have a script and a key. So that a script means that we can like do some programming, do some opcodes, do some logic that needs to execute to true, so that we can spend the output, and like a key, our private key, and with which we sign stuff, so that not just everyone can spend our output. So only the one who's actually supposed to be able to spend it can spend it. And by destroying existing locks, existing outputs, we are able to create new outputs, new locks, which can have scripts and need signatures from different keys to be able to be spent. And that's the concept of UTXO-based chains. We have outputs, we destroy them and create new outputs. And for destroying outputs, we need to make sure a script executes to true in the end. And for that, most usually, there is some kind of signature check in the script. So we need to have a private key with which we sign the transaction so that our script executes to true in the end. When we want to have scripts in our UTXO-based world, what we do is we use opcodes. Opcodes are basically operations that we tell the node what it's supposed to do when executing the script. Like a programming language, it's just that it's a little more low level than your usual Python, JavaScript, C++, whatever. And these opcodes tell the node what to do. In the UTXO-based world, those opcodes are pretty sophisticated. And I put some like rather sophisticated examples on the list here. Like for example, opchecksig is an opcode to check signatures, verify signatures. Object multisig is an opcode to verify multisig. And when you think about it, it's a pretty sophisticated thing to do. When you have a set of keys and like 2 out of 3 need to sign a transaction, and then you do object multisig, that's pretty sophisticated logic. With like you have a set of keys, 2 of them need to sign. There can be different combinations. You have the multiple signatures. It's a pretty sophisticated thing to do. And the Element and Bitcoin networks, node softwares do that for us. So it's a very sophisticated operation. And same thing with op SHA-256, which creates a SHA-256 hash of like some data that we have in our script. Also, think about implementing SHA-256 from scratch. It's a pretty sophisticated thing to do. So what I'm trying to say is that in the UTXO-based world, we have sophisticated opcodes and strong primitives with which we can build our scripts. When we want to have the script or like an address to send to, what we usually do is we write a script of operators, for example, a public key and an opchecksig verify to check a signature for a public key. That script we take and then we hash it. And based on that hash, we create an address. So basically, every address you have ever used in any kind of context is created via this system. There is some special kinds of addresses, and I'm gonna get into the details later this afternoon, but that's the basic concept. That you take a script, hash it, and that's your address. When we talk about the account model, there's a stark difference. We had the UTXOs with the unspent transaction outputs that are destroyed and when used in inputs in new transactions, which then creates new outputs. When we look at the account model, it's very different. In the account model, you have an address, and this address can be a piece of code. That a piece of code has a very specific address on the blockchain that when you talk to it, executes code. With the keys on my little graph, I signify that the keys are users with a private key that sign transactions, and all those people, and maybe even other contracts, interact with the singular address at a specific place in the blockchain with a specific address. So we don't destroy anything, we don't create new things, we literally talk to existing addresses we know and interact with them by sending data to those. So the mental model is very different. The next big difference is that when you talk about opcodes in the account-based world, they are much more low level. We had like the check multisig of SHA-256. In the account-based world, you have very low level opcodes, like for example, multiplying, dividing, jumping to different pieces in the code. It's like assembly language in your normal CPU. Much more low level, and you get the advantage of it being Turing complete. So anything you want to program, you can program and execute on-chain. But the downside is that the primitives are not as strong. For example, if you want to have a multisig on Bitcoin, you have the object multisig opcode, which is fairly easy to use. Give it some public keys, tell it how many signatures you need to be able to spend it, and that's your multisig on Bitcoin. If you want to have a multisig in an account-based world, I wish you best of luck, because you have to build the whole logic yourself. And there have been many screw-ups in the account-based world with even easy stuff like multisigs. You can look up the parity multisig bug, where they lost millions of dollars with the contract that was supposed to be a super great multisig. but they screwed it up in the implementation, and all the money was lost. So when you work with an account-based chain, you usually have to do everything yourself or use third-party libraries that hopefully work, else you're pretty much screwed. Meanwhile, in the UTXO-based world, you have much stronger primitives for the usual blockchain programming things, like, for example, hashing, checking signatures, and these kind of things. I also want to quickly show what kind of networks exist for the UTXO and the account-based model and compare them a little bit. Like, when we talk about UTXO-based chains, the first example is obvious. We have the Bitcoin chain, which is proof of work chain, has 10-minute block times, is pretty much as decentralized as it gets. But when you are a developer, the main, at least in my opinion, the main downside of Bitcoin, the blockchain, is that it gets barely any updates. The last change we saw in Bitcoin was the Taproot soft fork in 2000, like a couple years ago. I don't remember exactly when, like I think 2020, 2021, something like that. And ever since then, it has been no changes for the devs, pretty much. A little minor things here and there, but nothing major. And for me as developer, that can be a little bit boring because nothing changes and I'm very limited by the things that can be done. The next big UTXO chain that's relevant is the Liquid network, which is the premier public network built with the Elements code base. And just to reiterate the properties of Elements real quick, the blocks are signed every minute. The block signers are a global federation of different companies and stakeholders in the network. The Liquid Bitcoin has a one-to-one relationship with actual Bitcoin. So the 1 LBTC is worth exactly 1 actual Bitcoin. In the Liquid network, you have confidentiality by default. And the cool thing about Liquid as developer is it's a fork of Bitcoin, the code base. So that means that everything that works in Bitcoin works in Elements, probably without changes or very minuscule changes, but you have much more features in Elements. For example, Taproot was deployed in Elements before it was on Bitcoin. On Elements, we also have so-called covenant opcodes already. And I'm not sure if you followed the last couple debates about covenants on the Bitcoin chain, but they exist on Elements already, and they pretty much jumped the gun and are most likely implementing features that are coming to Bitcoin sooner or later before they actually get forked into Bitcoin, which is super cool as a developer because you can experiment with what's probably the future of Bitcoin itself. There are a couple projects that built their first MVPs, first iteration products on Liquid because they have the features of the future, so to say, already available, and backporting the logic from Liquid back to the Bitcoin blockchain is very doable and not that hard because it's the same primitives, just a little bit ahead of its time. When we talk about the EVM, the obvious example is Ethereum itself, which recently or somewhat recently switched from proof of work to proof of stake. They pioneered the Ethereum virtual engine, and by that, pretty much all account-based blockchains are derived from the Ethereum virtual engine, more or less. All of them take inspiration from them. One could argue that Ethereum is like sufficiently decentralized when it comes to people running nodes and staking. And a fun fact is that Ethereum exists because the founders of Ethereum thought that the Bitcoin scripting is too limited. So they were frustrated with the Bitcoin ecosystem and just created Ethereum to have more scripting capabilities. Yes. We could argue about that. We can argue about that later. But like, if you compare it to, for example, Binance Chain or Solana or something, I'd say it's the least bad actor. There are many things that are way worse. And when we talk about Liquid and like federated chains that are running in federations. There's also like equivalents in the EVM world. The most prominent one is Hyperledger, which is pretty much the same thing as Liquid, just for the EVM world, where you have signed blocks with custom configurations for custom networks, and there's also software to do confidential transactions in a way. So the concept of Liquid is not that far-fetched. Every ecosystem is doing their own kind of Liquid-esque thing. It's just that in the Bitcoin ecosystem, Liquid is the most prominent one. Things like Hyperledger are more used for these blockchain, not Bitcoin kind of things by big corporations, while Liquid is this more open federation for everyone to use. And I want to quickly talk about the technological improvements that are happening on both sides, in the UTXO world and in the account-based world. The first big thing that Liquid brings to the table is confidentiality. These confidential transactions where you don't see the amounts and the assets that are being sent, it might not sound that amazing at first glance, but it's pretty great. And I think Chase already showed the tweet earlier, but I want to reiterate on it. This is a tweet from Paolo Adornio. He is the CEO of Tether and like CTO of Bitfinex. And they created an asset issuance platform called Hadron, which features Liquid simply because Liquid is the only production-ready network that has confidential transactions. And if you think about it, that you want to issue some token, like, I don't know, some real world asset, like tokenized whatever, or issue your stock as a token, confidential transactions are pretty cool because you don't want the world to know who owns your shares, who owns how many. That's like private information of you and the people you transact with, and not for the world to know. So confidentiality might be overlooked when you hear about it the first time, but it's a super awesome feature, especially for issuing tokens that are not that that are not distributed as widely as Bitcoin. The next big thing that got into Bitcoin and Liquid the last couple of years is Taproot. And Taproot also got lots of hate and isn't talked a lot about when it comes to like technological improvements. But I think it's super awesome. And I'm going to talk a lot about it later when I talk about what I do. But as a quick overview, Taproot allows you to hide scripts that you put into the address. So we had the idea of you have a script, that script you hash, and that's your address. With Taproot, you can do much cooler things. Like you build a tree of different scripts, and you only have to show the one script you actually execute and not all the others, which is amazing because you can have a million different scripts, a million different spend conditions, but you only ever have to show the one that you actually want to execute. So your huge program with lots of different if-else statements can be ripped apart into different scripts, and you only ever have to show and make the one piece that you actually execute. That one you show to the blockchain and to the world. The rest stays hidden in your wallet, and nobody apart from you and the people you share your wallet data with will ever see it. And Taproot allows for Schnorr signatures, or rather requires Schnorr signatures, which are super cool because you can do novel signature schemes. The most prominent ones are Music and Frost, where Music is already like production ready and used in the wild. Frost is still more this experimental thing, but the idea is by doing these new schemes that you can have super cool new multisigs that are insanely efficient when it comes to using blockchain space. In the old way, we had multisigs as scripts. For example, you have a script, you push 3 public keys into the script, and then tell the object multisig opcode, hey, you have 3 public keys there, two of them need to sign for you to return true. With Music and Frost, what you can do is have communication outside of the blockchain, collect partial signatures from all your multisig participants, aggregate them into a single signature, and only that single signature you publish to the blockchain. So you have a hidden multisig from the eye of the public, but you still need to have multiple signatures from different keys. You compress them, so to say, you aggregate them into a single signature, and that single signature you show to the blockchain, which is also something that doesn't sound that great, but when you build with it, it can be super efficient, and you can combine those two features with like this hidden multisigs, this aggregated multisigs and the hidden scripts. You can build super powerful contracting systems for multiple parties to have spending conditions, but nobody ever needs to know about them. And in the happy scenario, it just looks like a normal single sig spend with a single signature on the blockchain. I'm going to show that off when I talk about the Boltz stuff later, and it helped us save hundreds of thousands of dollars in blockchain fees because we are super blockchain efficient. We only need a very little space on the chain instead of publishing our huge scripts all the time. And one other cool thing that I also already touched on, but I want to stress it again, is that Liquid has covenants. And covenants, we have a new primitive when it comes to scripting with Bitcoin-esque chains. When we have a script, the script can have conditions. Like, for example, you need to sign with a specific private key for the script to return true. Or you need to know a secret for a script to return true. With covenants, we can inspect the transaction that spends our UTXO with the script. So the script can say, I can only ever be spent if the first output of the transaction I'm spent in goes to a specific address, or only ever be spent if the second output has a specific value, or I can only ever be spent if the second input of the transaction I'm spent in is a specific outpoint. So we can have a look in our script at the conditions where the script is being spent at. And that's a super powerful primitive for building more complex systems. And it pretty much allows for not just off-chain data as proof to be able to spend it, but also restrict the way it can be spent with on-chain data, and like tying specific outputs to specific conditions and ways they can be spent. When we look into the future of Liquid, the next big thing that's going to happen is called simplicity. And simplicity pretty much ditches the entire opcode system and introduces a new language called Symfony into the mix, which is like a complete revamp of the way that people program on chains. It's trying as hard as possible to learn from all the mistakes of the Bitcoin chain in the early days, the Ethereum world, the Solana world, and whatnot, and tries as hard as possible to not repeat the mistakes by having a new language for blockchain development that can be formally proven. As in, you can literally make sure that the contract that you've written is specifying exactly the spend conditions that you want, and you didn't overlook anything and make any mistakes. It's not live yet, but this is going to be like the future of scripting on Liquid for sure, maybe also one day on Bitcoin, and it's super cool, and I'm really looking forward to that. Yes. Will be Turing complete? Turing complete? No. The only thing you cannot have in simplicity, as far as I'm aware of, is these unbound loops and like recursion. Those two things it doesn't support. Apart from that, I think you can do literally anything. If you just create a transaction big enough, you can do whatever you want. The only thing you can't do is unbounded loops, because they are like really tricky for the interpreter to manage. And what do you do if you just never break the unbounded loop? You have For security reasons, yeah. And also it's really hard to formally prove unbounded loops and recursion. And when you look at like these smart contracting languages and other chains, unbounded loops and recursion is somewhat uncommon in them because like the complexity is really high and you get to make mistakes a lot. Plus it's expensive to run those things. So technically, no, not Turing complete, but you should still be able to do whatever you need to. When we look at the EVM, ever since the launch of Ethereum, they didn't change much. Because the opcodes are so low level, they only did minor optimizations here and there, but no major thing changed in the EVM world in the last 11 years. Pretty much they are done trying to improve the ecosystem. They did some changes to language, some optimizations, but the focus of the EVM world has been on scaling and proof of stake. Since the focus of the EVM world has been on scaling, okay, yeah, I guess time for a break? Sure, let's do it. Is the scalability of the UTXO model versus the account-based blockchain model, especially with a focus on elements, where when you have UTXOs, the transaction execution you can parallelize really easily. Because if you think about it, these unspent transaction outputs are only ever referenced once when they are destroyed and then they are gone. So you have a pretty easy way to parallelize execution and transaction verification. The limiting factor when it comes to scaling UTXO-based chains is the UTXO set, which means the unspent transaction outputs that exist at a given point in time. So if everybody just creates 1,000 new outputs, that's going to bloat the chain because the node needs to remember all of those outputs. But the easy fix for that is consolidation, which everybody does anyway, so that's not too big of a concern. If you just keep your wallet in check, and most wallet softwares just do that by themselves, everything is going to be fine and the chain itself won't have crazy UTXO stack growth. When we talk about the scalability of elements, the one thing that comes to mind is the confidentiality, meaning the transaction proofs of the amounts and the assets and that everything is in order. Right now, that's actually pretty slow, especially on mobile phones. It can take a second or maybe 2 or even 3 to create the necessary proofs to create a confidential transaction on a low-powered CPU. But there is a light on the horizon with Bulletproofs Plus, a new proofing scheme for these confidential transactions, which is much more efficient and also has much smaller proof size. So in the future, hopefully in a year or maybe 2, it's going to be much faster to create and blind elements transactions. So the scalability limitations are not that huge. And since it's a federated chain, there is no block size limit, and we can go as big as need be to just have the sheer throughput on elements and liquid. When we talk about the scalability of these account-based systems, the tricky part is the state, meaning the permanently stored information on the chain, which includes code, balances of who owns what token, and other arbitrary data written into the chain. And if you check out the chart I have on the right-hand side, this thing is going up only. While on the UTXO-based chains, we have consolidation, which decreases the UTXO set, so less UTXOs exist. On these account-based systems, you pretty much never delete your state. You never clean up after yourself, and this state just blows up and balloons into infinity and just becomes unscalable. And right now, there is no way to properly address this, apart from just deleting data after some point in time, which is a really nasty side effect. And Yeah, scaling account-based systems is really tricky, while on the UTXO-based sites, we have simple fixes for simple problems. And the last point I want to touch on is the asset issuance, which is like maybe a little bit of an unfair comparison, but when we look at the chart, it's like you have in Elements the asset issuance as a native feature of the chain, so it's natively supported everywhere. You have management tools like the AMP, open source ecosystem, which also ports the same standards. You have the confidentiality, which is pretty much an Elements only feature. It's opt-in. If you want to use it, you can use it. And it's a great feature that just comes out of the box. And you have the scalability of a UTXO-based system where you don't have endless state growth that blows up your entire node and makes it infeasible to run. And with that, I conclude the comparison between EVM and the UTXO-based model. And next, I want to talk about what we do as a business at Boltz and how we use the latest and greatest features of Bitcoin and Elements. And yeah, let me switch the presentation real quick. So at Boltz, we have one mission. What we want to do is connect the different Bitcoin layers. Be a bridge in the Bitcoin ecosystem so that you can move your coins free and as fast and efficiently as possible between the Bitcoin layers. And layers, I mean, of course, like the Bitcoin main chain, the Bitcoin blockchain itself, Lightning, Liquid, and as of somewhat recently, Rootstock. And when we talk about these layers, they have very different capabilities. On Bitcoin, you have the opcodes. On Liquid, you have also the opcodes, but in a more advanced fashion with some extra features. On Rootstock, you have pretty much the EVM. And Lightning is its own kind of completely different beast to tame with like basically no scripting capabilities. So when we want to bridge and have an atomic exchange of Bitcoin from one layer to the other, what we need to do to have like a common denominator for all of those four, what we need to do is called HTLCs. Hash time lock contracts are the only contracting primitive, the only scripting primitive that exists on all four of those. The limiting factor is especially Lightning, because the only thing that Lightning can do is send payments, and these payments are sent via HTLCs. And since that's the only thing we can use on Lightning, that's what we have to use, and that's what we have to implement on all of these other layers. What do we need for an HTLC for a hash time lock contract? A hash lock and a time lock, as the name indicates. And what that basically means is a hash lock is that you lock coins in a script with a hash. And to unlock the coins, you have to show a secret to the script. Meaning that you take a secret, you hash it, you put that hash into the script, and to be able to unlock the coins, you have to show the secret to the script. And time lock is, I think, pretty clear. It can only be spent after a certain amount of time. So it's locked for a certain amount of time. And that's how all payments on Lightning work. When Bob wants to pay Carol by routing via Bob, Alice wants to pay Carol by routing via Bob, what Alice does is send an HTLC from her node to Bob's node, and Bob does, after that, send an HTLC from him to Carol, and you have this sequence of HTLCs. Carol, in the end, when she receives the HTLC, releases the secret of the hash lock, and the payment goes through. In case of some HTLC getting stuck, some node being offline, or like bad things happening, there's always the time lock component. And if the secret isn't revealed in time, the time lock is enforced and all the coins go back to where they were before. So either these scripts are unlocked via a secret, the hash locks, or after a certain amount of time, the time lock. And what we do with our swaps is we take that exact same primitive of the hash time lock contracts, but instead of forwarding the Lightning payment to a different Lightning node, is we take that HTLC and forward it on chain. We take that contracting primitive and forward an HTLC with the same hash lock and the same time lock onto the blockchain, in this case to Liquid. When you want to do that, when you want to push such a HTLC on chain, you need to write the script. And I'm gonna show the Bitcoin version of the script, but it works the exact same way in Liquid, because Bitcoin script is exactly the same as Liquid script. It's just that Liquid script has a few extra features, which we don't need for our simple HTLC example. So this script is the same for Bitcoin and for Liquid. The first iteration of the script that we did was in SegNet version 0, and that was our script. Let's go over it real quick. We have the opcode opsize, which means that the first element that we push to the script as parameter, let's get the size of that. Then we push bytes 20 on the stack. 20 in hexadecimal is 32 in like decimal. So we get the value 20 in the stack, and then we op equal, meaning the first parameter of the script has to have the length of 2. In the case, we go to the hash lock segment. There's an op if. So if the first parameter of the script has 32 bytes length, we go into the if, we take that variable, hash it with hash 160, push the hash lock, the hash, onto the stack, do op equal verify, meaning that we verify that the op hash 160 of the parameter, so the hash of the parameter, is the same as the locked hash lock value that we expect it to be. And if that's also the case, we push the public key of the party who is supposed to claim the HTLC on-chain onto the stack. In the very end, after we end the if-else statement with an object sig opcode, so we take this public key and verify the signature in the end. Yes, question.
Programming language or is
Come again?
well this is programming language or
Oh, this is Bitcoin script. This is Bitcoin script, like Bitcoin opcodes. That's what you can do with the Bitcoin scripting language. So to reiterate the concept, if the first parameter of the program has a length of 32 bytes, we check if it's correct against the hash that we expect it to be, and if so, we push the public key of the party who is supposed to claim the HTLC and verify the signature against that. That's the hash lock part. If the first parameter is not the length 32, we drop it, we just ignore it. We push the lock time as blockade onto the stack, and then do object lock time verify to make sure that the time that we expect has passed already. So this is the time lock. We drop the result of object lock time verify, and then we push the public key of Boltz so that we can get our coins back in case the other party is just not claiming their coins. That's the time lock part of the thing. But when we look at this script, it's not very efficient, because for every single on-chain HTLC, we have to take this whole script, hash it, create an address for it, and when we want to spend it, we have to show the whole script, although we just execute the if or the else path. So we push a bunch of unnecessary code and opcodes to the chain. This is where Taproot helps us, and I already mentioned it that with Taproot, you can do a bunch of fancy things to avoid pushing all the data to the chain. And that's what we did. The first primitive we used is the Schnorr signatures with music 2. In the old script, we have 2 different public keys. one of the other party, of the user, and one of ours. What we do with Music 2 is we have two keys, one of ours, one of the user, and those two keys we combine into a single one. We aggregate two keys into a single public key with this Music 2 signature generation scheme. So if we and the user agree completely on what's about to happen and what is supposed to happen, we can take our two keys, combine them, and together sign off on a transaction. So if we do that, it looks like a normal single sig spend on-chain. It's a hidden multisig, and the communication happens completely off-chain via HTTP or whatever transport you want to use, and the blockchain usage is minimal because you do all the tricky stuff of coordination, not on-chain via contract enforcement, but off-chain via signature aggregation. And the other cool thing we did is that in case that we and the user don't agree, we still have to have the script in there to be able to force the coins to the destination where they are supposed to be. So we still have to have the script. But instead of having the whole script and an if and else path, what we do is we rip them apart into two different pieces and build a tree out of them. Our tree is not deep, there's just one layer to it because we only have two branches, two different possibilities to execute things. The left side is the hash lock and the right side is the time lock. And if you look closely, those two are basically the if and the else path that we had before. It's just in two different scripts now. So the hash lock and the time lock, same thing, just now in two different scripts. And when we want to spend those scripts, we don't have to show the whole thing with an if and an else anymore. We just show the part that you want to execute. So if you want to use the hash lock and prove you have the secret, you just show the hash lock script. If we want to get our coins back and execute the time lock, we just have to show the 4 opcodes and a little bit of data of the time lock and not the whole script. That also saves quite a bit of chain space in the non-cooperative path in case we cannot do a cooperative signature. What we do then is combine those two. So we have the key path spend, where you have the two public keys that you aggregate into a single one with which you can spend. And that aggregated combined public key, you tweak its code, basically multiply with the hash of the tree of scripts. That means you can spend both ways, either by signing together and agreeing on what's supposed to happen, or in case you don't want to agree or can't agree because someone is trying to cheat, you can just show up to the chain and say, hey, this public key was multiplied with this tree of scripts. Here's the script I want to execute. Here's the proof that this is actually the case and the script is valid for this public key, and execute the script. So you have the exact same ways to spend as by having a whole big program, just that you can be more selective about what you want to execute, which allows you to build bigger structures and have them more efficiently, more selectively published on the chain. Only what you need needs to go there and not everything all the time. So that's how we do these swaps. We're taking the Lightning primitive of hash time lock contracts and publishing them to the blockchain in the exact same way a Lightning node would forward payments to their other Lightning peers. With Taproot, we made those as efficient as possible and use as little chain space as possible by using all the latest and greatest advancements in the Bitcoin space. But what is that useful for, especially on Liquid? The one use case that we found, or rather that found us, is wallets. Just to name like the bigger ones, we have the Bull Bitcoin wallet, Aqua, and Blitz from Blake, who's going to do a session tomorrow and show you all the details on how it works and why it's a good idea or might not be a good idea to do that, but he's going to talk about that tomorrow. And yeah, these wallets use atomic swaps with the exact tag I just went over, abstracted away from the user, and use a liquid wallet plus the HDLCs on-chain with the scripts and whatnot to do Lightning payments without actually running a Lightning node in the app. Basically, when you have a look at, for example, Aqua, you have the Bitcoin balance, Tether, which we ignore for now, and what they call layer 2 Bitcoin, LBTC. That thing is effectively a liquid wallet, but what UI allows you to do is, for example, paste in a Lightning invoice or scan a QR code of a Lightning invoice. And what it will automatically do in the background is create a swap with Boltz. Create a swap with Boltz, send from its liquid wallet to fund the swap, and we will set the Lightning payments and claim the liquid Bitcoin like a Lightning node would claim an HDLC that is forwarded via it. And saving for receiving. If you go to receive an Aqua, select Lightning, enter an amount, and click create invoice, it will create a swap account, and all the on-chain HDLC stuff will happen behind. So basically, the entirety of Lightning complexity is abstracted away in the Aqua wallet. It feels like a Lightning wallet to the user, but in the end, it's a liquid wallet that just does swaps between liquid and Lightning when needed. And the question is, why would you want to do that? Why do you want to have swaps between liquid and Lightning? And the reason is simple. There's so many different technologies built on Bitcoin right now. You have the Bitcoin main chain, you have Liquid, Rootstock, Arcs, Fedi, Cashew. And in the end, the one thing that exists on all of them, that you can send to and from on all of these networks, is Lightning. You can swap from Liquid to Lightning. On the main chain, there's actual, like real Lightning. On Rootstock, you can swap to Lightning. Arc has a Lightning swap. Fedi and Cashew, you can go in and out with Lightning. So Lightning is becoming the common language of the Bitcoin ecosystem. Everyone interacts with each other on Lightning seamlessly, which is why this is such a cool thing for Liquid. By Liquid having swaps to and from Lightning, you can go from Liquid to anywhere else pretty much immediately and whenever need be. So that's the why. And I'm super happy about Samsung approaching us like a little over a year ago to get these swaps into Aqua, because it pretty much created a new kind of Lightning wallet that has these swaps and allows you to interact with your Liquid wallet with any of the other Bitcoin ecosystems and layers. It's pretty much the bridge from Liquid to the rest of the Bitcoin world. And in the end, I want to do a quick demo and show you on a code level how all of the key path, script path kind of things work, and go over a little bit of code just to have a clearer understanding of what's happening behind the scenes and not just these abstract overviews. All right. Yeah, I'm gonna zoom in a sec. Hold on.
What to the close? Oh,
All right. Let's have a look. We're just gonna ignore all those imports and JavaScript shenanigans, and let's have a look at the actual swap stuff and what's interesting. We're gonna use the Boltz API. That's our mainnet endpoint. And because we're playing around on mainnet, I'm just gonna swap 1,000 sats, because if it goes around, whatever. This is an address of my green wallet. Actually, let me get the new address real quick. No, the internet is really bad today. Anyways, while that's loading, we're gonna use the network liquid, which is the liquid mainnet. This initializes some of the libraries and cryptographic primitives to do blinding. We're gonna create our 32 bytes secret. In our case here, just 32 random bytes. And because this is not actually a wallet, but a random script, we're gonna make a random public key. Yeah, seems like the blockstream servers, yeah. The blockstream servers are down right now, so I can't get into my fucking wallet. We'll just use my old address and call it a day. All right. We call the Boltz API, and we want to do a reverse swap. So a swap from Lightning to Liquid. For like 1,000 sats, our invoice amount, to LBTC, which is Liquid, from Bitcoin, Lightning. Our public key, we give Boltz our public key as hex string, and we give it the SHA-256 hash of our secret, but only the hash, not the actual value. Gonna console log that to see what's going on. We're gonna open a WebSocket to get updates about the swap and see, hey, something happened, that we can react to that and do necessary actions to complete the swap. Whenever we get the WebSocket message, we're gonna parse it and print it out when it's of relevant to us. When a swap is created, we send out status updates to inform the client about what's going on. For example, swap created means, pretty self-explanatory, it was created. Transaction mempool is the next state we're going to be in, and it means that Boltz sent the on-chain coins and they are ready to be claimed. So the HTLC was created, and now everyone is waiting for our script here to do something and claim those on-chain coins and get them into their wallet. What we're going to do here is the signature aggregation. So we're not going to enforce the script, but we're going to do the magic 2 public keys into 1, 2 signatures into 1 aggregation thing. For that, we create a new music session. Music is the protocol that is used for that cryptographic magic to aggregate signatures. And we're going to tweak our music. So we're going to tell our music about the scripts that could be executed, but we just won't in this scenario. But you still have to tell about the music about, hey, these scripts could be in there, so be careful with that. We pass the transaction that Boltz sent on-chain, detect where in which output our swap is, error hard in case it can't find it, so hopefully that doesn't happen. And then we create a claim transaction. With the output, our keys, the pre-image, we say cooperative true because we just want to see the signature on chain. We are using taproot, spend this transaction hash, and we are blinding with this private key. We're gonna send to my destination address from above, and we're gonna blind our output with the blinding key of the address. That will give us an unsigned transaction. And the unsigned transaction, we still have to and a signature too via the music and the partial signatures that we aggregate. For that, we call our endpoint with, hey, please sign the zero-ref index, so the zero-ref input of this transaction. This is the pre-match to prove that I actually know the secret. And this is my music session information. We tell the music about, hey, let's do some stuff. Let's aggregate some data. Tell it what we're going to sign. In this case, our transaction that we hash for this special music thing. We add the partial signature of the other side, sign our partial part, and in the witness of the transaction, in the input, we put the aggregated result. That we're going to broadcast. And when everything works well, we're going to get this invoice settled, status update, which means the swap went through and everything is fine. Log that out, close the WebSocket, and end the script. And that's what we're going to try real quick. Let me try the green wallet again. Hopefully it loads this time. If it doesn't, because it's just going to check it out in the Block Explorer. So we created the swap, got an invoice, and bunch of extra information. This is the tree with the claim leaf is the hash lock, refund leaf is the time lock. And this is like the Bitcoin script as hex. A binding key, the address in which the coins will be locked. A refund key that is going to be used in the time lock scenario when the time lock will be available and how much will be sent on chain. Swap was created just fine. Let's pay the invoice. Send. Fuck. Timeout. Had that before because the internet is really flaky. Do it again. Timeout. Oh, come on. Let me switch to my hotspot. Live demos are always horrible because everything that can go wrong does go wrong. So let's try this again. Oh, come on. Am I being stupid? Oh, what's going on? Like, this works just fine. What the fuck? Yeah, the internet really, really, really hates me right now. I don't know. What I can do is maybe it's gonna work in the browser. So basically on our website, this exact same thing happens.
I think that will wrong work because I send some chat. They are likely to Alpha and
Went through?
1 hour later. I think that don't work.
Really?
Yeah. I send some chat via Lightning to my wallet subscription to Alpha One.
Doesn't show up?
And no, it's weird. I received after 1 hour.
After 1 hour, yeah.
And my status is kiwi.
Cute. Yeah, that's about a Satoshi bug. That's a
Yes.
bug about Satoshi. All right. What I can do is show it in the browser because that's gonna work just fine. Hold on. Our browser is basically, our web app is basically using these exact same libraries and doing the exact same thing. Just in the browser with a nicer UI than the CLI. It's showing us the invoice, which we can pay again. Come on. Yeah. send, and he will get to see the WebSocket updates of, hey, swap update of this ID. We're gonna claim this cooperatively, private key and pre-image, and we broadcast the transaction. Let me check out the transaction and how it actually looks on the chain. It's not loading. Yeah, I have not turned the Explorer though. So this thing did exactly that, claiming taproot swap cooperatively, meaning that we did the signature aggregation and no script was revealed on the chain. Let's check the transaction. And when we look at the input at the witness, we only see these 64 bytes. And those 64 bytes are a signature. So the entirety of the scripts, the signature aggregation, there is nothing to be seen on chain. All there is a signature. And that this was a swap and all these script paths could have happened, you don't see those on chain. All there is the aggregated, tweaked public key and a signature that spans. That's it. If the server and the client were not cooperating, you could see the script that is being executed, but since everyone is just fine with the result and everyone is happy, they can agree on the signature that spans the coins. And this saves, misclick, hold on, and this saves quite a bit of chain space because we only need to push these 64 bytes. Imagine the whole script, including the if and the else statements from the very beginning. In 100%. No, hold on. Yeah. Imagine the whole script from the beginning would have had to be pushed on-chain every single time. This is so much more data than just the signature. So using Taproot and the aggregated signature saves a lot of chain space, makes a transaction cheaper, and therefore allows for the wallet use case. If we would have to do the whole script every single time, it would be too expensive to build a wallet with. But with these efficiency gains, a wallet use case is feasible because if you send from Aqua, it's only a couple cents in fees. If you receive, it's basically 5 cents in liquid network fees. And that's only possible because we are so efficient in just needing the single signature to spend the HTLC on chain. And that's pretty much what we do on Liquid. I would have loved to show that I actually received in my wallet, but it's not loading. And I guess that's why Pablo ran off so erratically to fix that. Yeah, that's pretty much it from my side. And I'm opening the room up for questions about Bolt specifically, about scripting, but also like anything else, Liquid or Bitcoin related, to make sure that there's no open questions left for tomorrow, because there's actually going to be some coding with Blake, and let's just clear everything up today so that tomorrow everyone can follow along and code just fine. Yes.
So whenever you talk low, it's not like it's rate dot codes. What were the additional features other than doing the hash though to all your route to pop keys?
Which other new opcodes came with Taproot or on Elements? On Elements, like, yeah, I can show the list of like new opcodes on Elements. Hold on. There's a nice markdown document in the Elements repo. The things that Elements added are the TypeScript, I think. Yeah, TypeScript block codes. The things that Elements added are a streaming SHA. So if you want to hash values bigger than the max stack size of 512 bytes, you can stream data into the SHA and have like a hash of bigger amounts of data. That's what Elements added. Then there is object from stack. which means that you can verify a signature against arbitrary data that you push on the stack, which is super useful for covenants. You have actual introspection covenants where you can check the outpoint you are spending, the asset you are spending, how much you are spending, and where you are spending to, which is basically everything that's being discussed for Bitcoin covenants. Elements has the most fully compatible, everything possible version imaginable. So basically all the covenant things are already there. You have also 64-bit multiplication, division, addition, and subtraction. So like 64-bit proper math opcodes. And some conversions, tweak verify, EC multicar verify, like pretty much every single covenant related thing that is being discussed for Bitcoin already exists on Elements, including 64-bit arithmetics.
Is that code a layer above, like using all optos will make new features, or I guess I don't know enough about opto, but I'm wondering if it's viable with like the architectures. So like I said, it's what it sounds like. They were in a horn, they were
These opcodes, basically in your Bitcoin node, there's a virtual machine that executes the opcodes. Think of it like a JVM. And the JVM runs on x86, on ARM, on RISC-V, whatever. Same thing for your Bitcoin node. If you run Elements D on your machine, all the opcodes run on it because there's a virtual machine in there that executes the opcodes. And these opcodes that are added to Elements, it just means that the Elements node software supports more of these instructions in its VM than the Bitcoin node software.
I have a question about HTLCs. With the HTLCs, you always have to fix the amount, right? There's no change output with HTLC.
With HTLCs, when you claim them, when you when you enforce them by claim or true, you always do the full amount. What you can do is batching, meaning that you can enforce multiple HTLCs in a single transaction so that you have a bunch of inputs of different HTLCs and a single output for like batching and efficiency. But in theory, it's always a self-spend because you go from the HTLC that you are allowed to spend to a wallet address that you actually own by just public-private key, which is like a sensible thing to do.
Maybe you can explain the differences between liquid script, tap scripts. Like
I know where you're going, yeah.
on a very high level.
So basically, what we had is Bitcoin op script that the Satoshi invented in the first version of Bitcoin. That's what we call like Bitcoin opcode scripting. Then we did SegWit in 2017, which changed which fixed a few minor bugs in the opcodes that Satoshi invented. With SegWit version 1, also known as Taproot, we got TapScript, which is basically the same thing as Bitcoin scripting way back in the day, but with another few bugs fixed. And with every new SegWit version 0, SegWit itself, SegWit version 1, Taproot, new opcodes are enabled. Like for example, with Taproot, the old object multisig opcode was removed, and there was a nice cleaner implementation added. So basically, we have different versions of Bitcoin script, namely Legacy, SegWit version 0, and SegWit version 1. And it's the same thing. It's mostly backwards compatible, just that the newer versions are a little bit cleaner and have bug fixes of the old code that Satoshi created way back in the day. And Liquid did change a few things in its TapScript, so SegWit version 1, the scripting language for Taproot, to like add the covenant features and the 64-bit arithmetics. So you have legacy Bitcoin script, Segwit version 0, TypeScript Segwit version 1, and the liquid version of that has some extra features. But in the end, it's full backwards compatible. Because if you, for example, take, I don't know, op inspect version is redefined as op success. So if you just take op inspect version and execute on the Bitcoin main chain, it will just say success and everything's gonna work. But like if you want to enforce those things, you need to use the right version. It's like upgrading your, I don't know, your computer from Windows 7 to Windows 10. Everything still works, but there's gonna be new features that you can use.
Where are these like what kind of use cases were you seeing?
For new use cases with covenants. Like the biggest thing that immediately comes to mind is Arc. Arc is like a new Bitcoin layer 2. And this new layer 2 is going to be much better if a covenant is enabled. Actually, the Arc Labs guys who are building the implementation did the first demo on Liquid because Liquid has covenants already. So it's really useful for prototyping and for like less interactive layer 2s. They want to have covenants. And also, like if we ever get covenants on the main chain, Lightning is going to get much better. In like 2018, Christian Decker proposed a new version of the Lightning Network called L2, which is going to be so much better in every single aspect. But the one crucial piece it's missing is a covenant. So basically, you can build everything you want without covenants. But if you have a covenant, it makes the protocol less interactive. So you don't have to exchange half-signed transactions all the time. You can just let the script with a covenant take care of the spend condition and don't have these half-signed transactions you need to store until the end of time.
Can you explain how water works? I know that.
Yeah, it's super tricky and nobody knows exactly how it's gonna work. But I can give the high-level rundown. So imagine all of us in the room are using the same arc, and everyone in the room has like 1 Bitcoin in the arc. When I want to send you some of my Bitcoin in the arc, what I do is I give up the right to my 1 existing Bitcoin, create my change output. Let's say I want to send you half a Bitcoin, create the change output for my half, and the other half goes to you. And everybody just sends each other Bitcoin by giving up the rights to get the ones that they own right now for new outputs. But none of these transactions, none of these new outputs are actually sent to the blockchain. What the Arc does is it creates such a taproot tree of different paths, different scripts, and these different scripts say who owns what. So basically what the Arc does is a big batching engine. Instead of publishing all transactions to the blockchain, it creates a big tree of who owns what, and all these state updates happen at the same time. So basically, instead of everyone broadcasting a transaction, the Arc server aggregates them all, compresses them into a single output, and that's the new state of the Arc and the ledger of who owns what. If you want to force your coins out of that single output, you show up with the script and the path, how to prove that the script is in there, and get your coins back. So it has unilateral exit, you can't force your coins out, and it's basically a big batching engine of all the transactions that happened since the last batch get updated in the tree of scripts. I hope that made sense. It's still very raw in the spec, and nobody knows exactly how it's going to turn out. But basically, imagine it as a big batching engine of every hour we aggregate all transactions that happened in the Arc into a single output that has hidden ownership proofs. It's like still like nobody has seen an actual Arc in production yet, so it's more of an idea than a real world use case.
You're saying you can prove the tree.
Basically, yeah. Like with Taproot, you have all these scripts, but you can't just show up with a random script to the chain and say, here, give me money, please. You have to prove that, hey, when this output was created, this script was in the tree that the public key was tweaked for. So you have to prove that, hey, this script is not made up, but it was actually included in the output when funds were sent to the output. That's what I mean by proof.
I can see that one.
Yeah, like Arc is pretty crazy stuff. Like if you have an HDLC with like 2 paths, sure, it's fun in games. It's like imaginable. With an Arc, when you have lots of people using an Arc, you have like 50 layers of tree structure, and yeah, it gets pretty complex, and nobody knows exactly yet how it's gonna turn out. So yeah, I'm really optimistic on Arc, but for the time being, if you wanna use like a simple lightning swap thing, Liquid is still the place to be, because like ArcNode, the software for it is like still join the wait list. Maybe we'll launch sometime. So it's not ready yet.
Kind of unrelated, but is Boltz planning on doing USDT swaps between Lightning and Liquid?
Tricky question. Like we are thinking about USDT. The one reason for which we have the assets that we have on Boltz, meaning main chain, Liquid, Rootstock, and Lightning, is that we can get in and out of those networks on our own. So you can like peg into Liquid, peg out of Liquid, open Lightning channels, close Lightning channels. If you want to go like USDT from Taproot assets or Ethereum to Liquid and whatnot, you cannot do that yourself. You pretty much have to ask Tether or Bitfinex to please do that for you. And I'm not super comfortable being at the mercy of Bitfinex to run our business. But for these assets we have, we can just like close a Lightning channel, have our coins back. Peg it off Liquid, have our coins back. If we do USDT on Liquid and have a bunch of Liquid USDT, we pretty much have to ask Bitfinex to please convert that USDT to USDT and Ethereum or Taproot assets. So we would be completely at the mercy, and I'm not super comfortable with that. So maybe one day, but not anytime soon. We're going to focus on the Bitcoin layers and stay Bitcoin only for the time being. I guess we're pretty much done for the day then, yeah?
What language is your library on the blocks? Library.
We have JavaScript, our reference, Rust, Python, Dart, C++, and some bindings for other stuff too. But it's mostly like we ourselves use JavaScript and Rust.